main person in Indo-French collaboration. They have helped a lot of Indian students to go in Paris, and faculties, postdocs, and he also helped a lot of French mathematicians to visit India also. So it's he was here in last January, just before the pandemic, and this year we are unable to move anywhere just because of pandemic. So once the situation normalize, we will always welcome to Patrice here. So, okay, sir, you can start the talk now.
Okay, thank you very much for the introduction. And of course, it looks strange to be home and at the same time in the lecture room in KSOM. I want to speak for this coming hour of a little thing we did with Purushottam Rat on the traces of powers of algebraic numbers. So to motivate our study, I would just want to indicate one context in which these powers of algebraic number and their traces occurs. And this is, sorry, I have to adjust. Yeah. So this is in studying the Diophantine behavior of powers of a number. So you take a real number, strictly larger than 1, and you consider the distance to the nearest integer. If I can. So let's denote double bar of alpha this distance. And we consider the sequence of all this distance for the power of alpha n. So this is actually, there is a conjecture by Hardy, which seems to be very difficult, which asserts that if the limit of this distance of alpha n tends to 0 when n tends to infinity, then alpha is a the PV number, a Piso-Vijayaraghavan number. And in particular, it is an algebraic integer. So Hardy proves the conjecture when we restrict to the domain of algebraic numbers. That is, if you assume from the beginning alpha to be algebraic, then if the distance to the nearest integer to alpha n tends to 0, then alpha is an algebraic integer and in fact a PV number. And what is interesting is that in this context, the nearest integer to the alpha n when alpha n is a PV number is just the trace of alpha n, the trace over Q. So this gives the idea to use a trace as a tool to distinguish algebraic integer from general algebraic numbers. And this occurs several times in Diophantine approximation. And this is a problem we have addressed. So there is, according to Bart de Smet, there is a result due to Polya. So Bart de Smet states the result which he attributes to Polya. And the result says that if the trace of alpha n, trace over Q of alpha n is an integer for all n, then alpha is an algebraic integer. Bart de Smet addressed then the problem. So you see here it's for all n. Address the problem of the smallest set that you can, where you can require the trace to be integer, which implies that the algebraic number alpha will be an integer. And he found the nice result, the following result. If you take alpha to be an algebraic number of degree d, so we denote d the degree, and we assume that the trace of a Q of alpha to the power I, for I running from a minus d plus 1 to a, so this is an interval of length d, starting from A minus D. And if we assume that A is large enough, so this means larger than this maximum of M plus MVP of M, where M runs between 1 and D, D is a degree, and P is any prime. So in fact, there is only finitely many prime because VP of M would be 0 otherwise. Then alpha is an algebraic integer. So you see we have really a minimal set where this is an algebraic, which ensures that alpha is an algebraic integer. The proof of the result is done locally, so by looking at the integrality of the number alpha for each place. And eventually, this is looking at the trace of 1, which is which is equal to the degree of the extension, so that is M here denoted. Then this trace leads to a contradiction by showing that it should belong, if under the assumption, to P VP of M plus 1. So it's too much divisible by P. And this contradiction proves the result, or proves that the number is integer at P, and you do this for all P. Now there is an example, which is just to take the m's, you take M a positive integer, and you take a m's root of 1 over P. So this is not an algebraic integer. And you look at the trace of the power. The conjugate of alpha, or alpha multiplied by roots of unity. And when you look at the trace, if n is not divisible by m, then these roots of unity add up to 0. And only if n is divisible by m, you find the mp to the minus nm. And now if you look at the first, so is it? If you look at the first value of n, where the trace is not integral, does not belong to Z, then you find that this is m plus m VP of m. So actually this shows that the theorem of Bart-de-Smet is the bound of A is sharp. And also it shows that you cannot allow gaps in the interval. You have consecutive integers to consider. Because here, of course, you have 0. So if you skip the bad value and put 0, you would get a contradiction. Okay. If I can change the screen, that would be nice. Yeah. So now, in view of this result, what's remained to consider is the case where you have a set of value of powers, alpha n, with integral trace, but for n running in a subset of n, or an infinite subset of n. For a finite one, we have seen with Bart-de-Smet. And then we have to consider now the trace for infinitely many n. And so, I'm sorry. So we can consider the following question, which actually generalize a little bit the result of Polya, because we consider here two numbers actually, alpha and lambda. We take them non-zero because otherwise the problem is trivial. And so we take two non-zero algebraic numbers, and let's assume that the trace of lambda alpha n, the trace to Q of lambda alpha n, is integral for all n. Then it is not difficult to show that alpha must be an algebraic integer, or the trace of lambda over Q of alpha can be 0. Of course, if we have this trace to be 0, then when you multiply by alpha n and take the trace to q, we still will find 0. So to prove this, we consider the, well, again, we denote d the degree of alpha over q, and lambda, we consider the lattice generated by the standard, the monomial basis, 1 alpha up to alpha d minus 1. Then we consider the complementary module, denoted lambda prime usually, for the trace to q. So this is the lattice which is indicated on the screen. This is the set of x in q of alpha such that the trace of x multiplied by any element of lambda is integral. Okay. And now, yeah. And now we make a few remarks on this lambda prime. That first, it is a finitely regenerated Z module. Actually, it is generated by the dual basis of 1 alpha, alpha d minus 1. A dual to the trace from Q alpha to Q. And the hypothesis that we have made, that the trace of lambda alpha n is in Z, implies that the module trace of lambda, trace to Q of lambda, multiplied by Z of alpha, is contained in lambda prime. Because if we multiply by any power of alpha, and we take the trace to Q, we will find an integer by hypothesis. Thus, Z of alpha being just contained in lambda prime is also finitely generated. And thus, alpha is an algebraic integer. Furthermore, the trace of lambda as noted is in lambda prime. And this lambda prime, because alpha is an integer, can be computed to be this module. This is Z of alpha multiplied by 1 over P prime of alpha, P prime alpha of alpha. This is the derivative of the minimal polynomial of alpha over Q evaluated at alpha. We will see expression like that later on also. So now we come to the subject I want to talk on. We take alpha and lambda. So the question is to take this lambda and alpha, two non-zero algebraic number, and now to wonder what's happened if the trace of lambda alpha n is in Z for infinitely many n. Does it imply that alpha is an algebraic integer? The question is, the answer is not so obvious. And in fact, we first restrict to the hypothesis that the trace of lambda alpha n is a non-zero integer for infinitely many n. So I insist, non-zero integer, not only integer. We assume that it is non-zero. And then under this hypothesis, alpha is an algebraic integer, in fact. Okay, so this is the first result. And the proof rests, well, imitate an argument, well, actually extend an argument of Pietro Corvaja and Umberto Zagné, who had an auxiliary lemma in their work solving two problems by Marler and Ménez-France. So the proof in particular uses the subspace theorem and also the Mahler-Skolem-Lesch theorem. Now, when we look at the previous theorem, there is a priori no relation between the lambda and alpha. We have not put any conditions that, for example, alpha belongs to Q of alpha or something like that. But if we pursue a little bit the argument, after the proof of the theorem 2, we can prove the following corollary. So we still have lambda alpha algebraic numbers. Here I assume alpha non-zero because lambda equals 0 is not much a problem. The hypothesis would be empty simply. The trace, we assume that the trace of lambda alpha n so belongs to Z and is non-zero for infinitely many n. So the same hypothesis as for in the theorem. And then the conclusion is that there exists integer L non-zero, the n cross mean the positive natural number. So maybe for you it's just n. And A is an integer in 0, L minus 1, such that the trace to Q alpha L of lambda alpha A belongs to this module 1 P prime alpha L of alpha L times the Z module Z of alpha L alpha minus L. So up to a little skip by this minus alpha L, this is essentially the complementary module of alpha to the power L. So I will not explain the proof is that the proof actually is done again by reduction modulo P for a suitable set of prime P. One remark is that in the proof of theorems 2, we had this hypothesis that the trace to Q of alpha n is non-zero. And actually, this is used in the proof because we use the subspace theorem and we need to assure that some linear form are not zero. But the example of the number alpha, which is 1 over square root of 2, which clearly satisfies that the trace is 0 for n odd, shows that if we don't put this hypothesis, alpha cannot be an integer. So if we don't put the hypothesis that the trace is not 0. One would think from this that maybe the case of trace 0 just occurs because of taking such square roots or some roots. But this is not the case. We have in the next slide, in the next slide again. We have the example of this polynomial, of this algebraic number, which is root of this polynomial, x4 minus 6, x squared plus 4. And the roots are just those numbers, plus minus, because you see that only x squared occur in the minimal polynomial. So plus minus 1 plus minus square root of 5 over square root of 2. The splitting field of this polynomial is real and has only 2 roots of unity, which are plus and minus 1. Now we set alpha to be the largest. I remember you that we assume alpha to be the largest root, let's say. And we check that the trace over Q of alpha to the odd power 2m plus 1 for any m is 0. Because of the plus minus sign, there is a cancellation, and this occurs for each odd power. However, alpha is not the root of a rational number. But we notice that alpha satisfies the following property. Alpha does not belong to Q alpha squared. So now we have seen what's happened if we have infinitely many traces which are integral and non-zero. Of course, if there are infinitely many traces which are integral, it can be that there are infinitely many which are integral non-zero, or the alternative is that there are infinitely many which are zero. So we have to investigate what's happened when we take the trace, when the trace, is zero for infinitely many n. And we have the following theorem in this context. So this is an equivalence between 2 and plus 1 statement. So we take alpha to be a non-zero algebraic number again, h to be the order of the torsion group of the splitting field of the minimal polynomial of alpha. So this, in the previous example, I pointed out that this was 2. And we set h prime to be the degree of alpha over q of alpha h. So in the previous example, we had alpha did not belong to q alpha squared. This means that h prime was strictly larger than 1. So now for lambda, any algebraic number, we have an equivalence between 1, which is a property we are studying, that is the trace over q of lambda alpha n is 0 for infinitely many n. And this is equivalent to the fact that there exists a in 0 h prime minus 1, such that the trace over q of alpha h of lambda alpha a is 0. If alpha is a non-zero algebraic number, a non-zero real algebraic number, then the two assertions above are equivalent to the third one, which is that the trace over q of alpha of lambda belongs to the union of the following q vector space. This is the sum for j running from 0 to h prime minus 1, different from I of q of alpha h times alpha minus j. So if h prime equal 1, as by the definition of h prime, this is the degree of q of alpha over q of alpha L, alpha h. This means that alpha belongs to q of alpha h. And then the set in the assertion 3 is just the empty set. So it's reduced to, it's an empty sum of sets, so it is just 0. For lambda equal 1, the assertion 3 is equivalent to h prime larger than 1. And this is what happened in the example before. Okay, so we have the following corollary, where we take lambda equal 1. We take alpha to be a non-zero real algebraic number, h to be the order of the torsion group of the splitting field of the minimal polynomial of alpha, as before. Then the trace over q of alpha n is 0 for infinitely many n, if and only if alpha does not belong to the field q of alpha h. Okay. And one thing which is, if we think of Bart de Smet result and Polya result, we see in Bart de Smet, if we impose that the trace is integral on some interval, then the number alpha is algebraic, and then the trace of alpha n is an integral for all n. Here we observe that something similar happened, but it is a little perturbed by the presence of lambda. That is, if the trace of lambda alpha n is zero for infinitely many n, then actually it is 0 in an arithmetic progression a plus of the shape a plus mh. H is a reason. Okay. So now we can combine, as suggested before, the theorem 5 on corollary 3. That is, we consider the case where the trace over Q of lambda alpha n is integral for infinitely many n. And this decompose, the proof which is written here, decompose in two. Either there are infinitely many zero, or there are infinitely many n such that it is an integral, non-zero integer. And when we put, so for the case it's zero, we use theorem 5, the equivalence between 1 and 2. And in the case of infinitely many non-zero integer traces, we use corollary 3. So the theorem reads like that. If the trace of lambda alpha n belongs to Z for infinity many n, then there exists, or it is equivalent, that there exists integer L in n, non-zero again, and A in 0 L minus 1, such that the trace of lambda alpha A belongs to this module. In the case 0, this is just 0 in this module, so it belongs to this module as well. But theorem 5 gives a more precise information. Sorry. Yeah. Yeah. So now I would like to make a few remarks on the parameters. And there is this L and A, and a priori we don't have much information, but we will see now that actually L and A can be determined quite precisely. So we let H prime to be the smallest positive, we want to find L first. We let H prime to be the smallest positive integer such that alpha to the H primes belong to Q of alpha L. So the conjugate of alpha over Q of alpha L are products of the shape psi alpha with psi a root of unity of order H prime, and which belongs to the splitting field of capital H of alpha over Q. In particular, H prime must divide the order of the group of unity, of root of unity in H. So H prime must divide H. And by the definition, H prime is the smallest such that alpha H prime belongs to Q alpha L. This implies that H prime must divide L as well. Otherwise, combining L on H prime, you would find a smaller power which belongs to Q alpha L. So we have H prime, which divide the GCD of L and H. H is always the order of the torsion group of H. And furthermore, since H prime divide L, we have that alpha L belongs to Q of alpha H prime. So this shows that Q alpha H prime, because we have one inclusion here and the other here, is equal to Q of alpha L. And so we may replace L by H prime, and H prime being a divisor of H. So in corollary 8, the L can be taken as a divisor of this order of roots of unity in H, that is little h. And of course, we replace A by its class modulo H prime. So you see that the choice of L in corollary 8 actually only depends on alpha. We have not introduced lambda so far. Now we have the dependency, the choice of the lambda will determine the choice of A. And actually, it is clearer to look for pairs lambda A together, because as we will see, there is a non so trivial link between lambda and A. Okay. Sorry. Here. So actually, the determination of this lambda and A will look a little bit like an algorithm. So you make some computation to write down the relevant Q vector space. So we call again D, but now it is the degree of Q of alpha over Q of alpha to the power L. So we assume we have given alpha and we have chosen L a divisor of H. And we denote by W0, WD minus 1 the dual basis of 1 alpha, alpha D minus 1, so minimal basis, relative to the trace from Q of alpha to Q of alpha L. So with this basis, we can write alpha to the A. We write it as the sum of AI alpha to the power I running from 0 to D minus 1. So this is expressing on the basis 1 alpha, alpha D minus 1. And the trace of lambda over Q of alpha, we write in the same way, but over the basis W0, WD minus 1. So we write it sum I equals 0 to D minus 1, BI, WI. And the AI and BI's belong to Q of alpha L, because this is the basis of Q of alpha over Q of alpha L. Then the trace of lambda alpha L of the product is easy to compute because we have chosen W to be the dual base. This is just the sum of AI, BI. Now, in order to fulfill the condition in corollary 8, that is to ensure that there will be infinitely many traces which are integral, we say that the integer A, which a priori which belongs to 0 L minus 1, and the algebraic number lambda must be so that the sum of AI, BI belongs to this module, which occurred in the statement of corollary 8. So again, the P prime alpha L of evaluated at alpha L times Z of alpha L, alpha L minus L. Okay. Yeah, for L equal 1, we recover we have to take A equals 0 because the interval 0, L minus 1 is just 0. And the algorithm just says what was expected, that the trace of lambda belongs to the complementary module up to some shift by a power of alpha. And well, I just wrote this slide to indicate that all these computations are quite explicit. If we write down the equation of alpha over Q of alpha L as f of x, that is a0 plus a1x, etc., plus xd, so it's a monic equation, the computation of the dual base wi is just a closed formula. So we take the basis 1 alpha alpha d minus 1, and the dual of this basis is given by this formula. Wi is equal 1 f prime of alpha sum k equal I plus 1 d ak alpha k minus I minus 1. And the second number is just because of the equation f of alpha equals 0. And reciprocally, if we have W, we can find the power of alpha. So now to conclude, I will show you two examples. Yeah. The first will be the primitive third root of unity. Then we have Q of omega, which is Q of omega squared. And Q of omega cube is Q, of course, because omega is a third root of unity. So it's contained and strictly the, the field Q of omega. It is strictly contained in the field Q of omega. And H is the number of root of unity in Q of omega. The splitting field of Q of omega, which is Q of omega. So this is 6, or 6 root of unity. And let's choose L equals 3. Well, actually, we would have to see L equal 1, 2, 3, and 6. But the most interesting in this case is 3. So the degree of Q of omega over Q, the Q should be understood as Q of omega cubed, is equal to 2. And we have 2, which is less than L, which is chosen to be 3. The minimal polynomial of alpha cubed of x, so there is a mistake here. There is no prime. This is not the derivative. This is a polynomial. This is just x minus 1, because alpha cube is 1. But if we look at the derivative of this polynomial evaluated at alpha to the cube, this is 1 also. So with this at end, one can compute the dual basis of 1 omega. This is W0 and WY. And we can write the trace of lambda over Q of omega as this expression with B1, B0 a priori in Q. So the trace a priori is an element in the Q of omega, and we write it on the dual basis with coefficient B0, B1, which a priori belongs to Q. But now, if we want to consider the fact that the trace of lambda omega 3n belongs to Z for all n in n, so again, as noted before, this is in arithmetic progression, then this would occur if the trace of the product lambda alpha n, so here alpha A is 1. So the trace of 1 on lambda, so this would be B0, because the omega 2 minus omega 2 over 2 omega 1 plus 1 is the dual basis. Then if and only if B0 is in Z, because the module, we can compute the module which occur in the corollary 8 is just Z in this context. Alpha cube is 1. And if we take now A equal 1, so we have the trace of lambda omega 1 plus 3n, which belongs to Z for all n. And now this is if B1 is in Z. In this case, of course, in the first case, B1 is in Q, can be any rational. B0, in the second case, B0 can be any rational. And in the third case, so we have to write omega squared as on the basis 1 omega. So we have minus 1 minus omega. So the condition is that B0, B1 are rational numbers. Just submit to the condition that B0 plus B1 is in Z. What's happened? Oh. Well, for L equal 1 and 2, we have D equal 1 in Z. And the result is just that this trace of lambda omega A plus Ln is in Z for all n, if and only if the trace of lambda belongs to this module. Actually, the case L equal 2 duplicate the case L equal 1, because we have two values, A equals 0, A equal 1, but in both cases, that will be the same condition. Just as the case L equals 6, which duplicates the three cases of L equals 3. We just copy the same and vary the exponent, put 6 instead of 3, and vary the exponent from 0, 1, 2, 3, 4, 5. And for 3, 4, 5, these are the same condition as for 0, 1, 2. Okay. So now, a last example. This is alpha. This is omega is again as before the third root of unity. And alpha is omega times square root of 2. Well, again, square root of 2 is real, so it doesn't bring roots of unity. So h equal to 6 again. And we have to consider the cases L equal 1, 2, 3, and 6. For result notation, we may set L lambda 0 to be the trace over Q of alpha of lambda, because in all the statements, you may have noticed that trace starts from Q of lambda alpha, but ends up with Q of alpha or Q. Then for this L on A, which belongs to 0, D minus 1 here, I restrict to D minus 1, we have the following equivalence. It will show up, I hope. That the trace of lambda 0 alpha A plus Lm belongs to Z for all m in n sufficiently large. So again, this is vanishing on an arithmetic progression of reason L. And this occurs if and only if lambda 0 belongs to this module. That is the sum. So we have to distinguish on the basis Wi, we have to distinguish I equal A and I not equal to A. And here we have the sum for I between 0 and D minus 1, different from A, and we just have no condition. So we put Q of alpha L Wi. But then for I equal A, we have a restriction on the corresponding coefficient, which must belongs to P prime index alpha L or evaluated at alpha L times Z of alpha L alpha minus L, multiplied, of course, by the basis Wi. I limited A to be D minus 1 because this gives such a statement where we have a correspondence between A and A. If A is between D and L minus 1, in case there is room for that, then we have to write the exponent alpha A on the basis. So on the basis up to D minus 1. And then the module we have to write here is more complicated. In this case, in the case we restrict to A to be less than D minus 1, the condition on lambda is just BA alpha L M0 belongs to the complementary module, which is written here. And the other BIs being free in Q of alpha L. So here are the data for the computation. So you have L equal 1, 2, 3, 6. And we have to write the field for L equal 1, this is Q, we write Q of alpha L. So for L equal 1, this is Q of alpha squared, Q of alpha cube, Q of alpha 6. So in this case, this is Q of alpha 6 is Q, of course. The cube is Q of square root of 2, otherwise for alpha squared, we have Q of omega. And for L equal 1, we just have Q of omega square root of 2. The degree are indicated here. And then we have the minimal equation of alpha over Q of alpha L. 1 here, 1 here, 1 here, etc. And eventually we also have the minimal polynomial of alpha L over Q. So alpha L, for L equal 1, this is just alpha. So we have the minimal polynomial of alpha here over Q. And here this is of alpha squared. Here this is of alpha cubed. And here of alpha 6, which is just x minus 8 because alpha 6 is 8. And then with this, you can compute the value p prime alpha L of alpha L and the dual basis. So in this case, the dimension is 1, so we have just W0. D equal 2, we have W0, W1, the same here. And for D equal 4, we have W0, 1, 2, and 4, 1, 3. Okay. So this is the end. I have just stuffed here a few references in connection with this lecture. And I thank you very much for your attention.
Thank you, sir, for the nice talk. So here you can see some of our new MSc students.
Yeah.
So any questions? So there is no question here, and the Zoom participants, any questions? I think there is no question in the Zoom participants. And then any questions in the YouTube channel?
There are no questions from the YouTube channel, Akhilesh. Thank you.
Okay. So there is no questions here. So let us thanks once again to the speaker. Thank you, sir. Thank you so much.